In this lecture, we're going to study resonances of sound waves in tubes, such as organ pipes and other musical instruments. These resonances are also known as standing waves, which we studied when last we talked about waves on strings. Let's review a little bit about what we learned when we studied string waves. First, let's not fail to recognize the importance of the so-called wave equation, which is true for any sort of wave, not only string waves, but water waves, sound waves, electromagnetic waves. The product of the wavelength and the frequency of the wave equals the speed of the wave. Now, what I show here is a standing wave on a string. One end is tied down, the other end is effectively tied down, but it is being oscillated at small amplitude, and the result is large movement at certain places along the length of the string. The left end and the right end are each nodes, and in between any two consecutive nodes there is an antinode. The letters always alternate from A to N or N to A. Never do you have two consecutive N's, never do you have two consecutive A's. Look at the broken red line that envelops one full wave length. The distance between that point and this point is one wavelength. What I want to point out to you is that the distance between consecutive letters, N to A, or A to N, those are the same values. We have one such distance, two such, three, then four that span the distance between those 2 points. One full wavelength equals 1, 2, 3, 4 of those A to N and A distances. So there are 4 of those to make one wavelength. So one of these distances, NA, equals a quarter of a wavelength. This is a crucial bit of information that we'll put to use when we study resonances involving sound waves. I show here a speaker next to a tube that is open at one end, closed at the other end. One such possibility for resonance in this tube is that there is an A at the open end, an N at the closed end, and then these additional behaviors along the length of the tube. You start with an antinode, then a node, then an antinode, then a node. At places in a tube such as this, in which there's an antinode, the air molecules are vibrating back and forth laterally, longitudinally, very vigorously. But in those places where there's a node, there's none of this horizontal vibration, as you could expect here, because that wall is rigid, that barrier at the end of the tube will not flex right or left. And so there's no oscillation, no vibration horizontally of the air wherever there's a node. So we have max vibration, no vibration, max, then no. Now, in this particular configuration, which is just one of virtually an infinity of different possible modes or methods or means of completing a resonance, we have 3 such segments, 3 such A to N distances. The sum of those 3 distances must add up to the length of the tube, which we'll call L. So triple the length of one of them equals the total length of the tube. Solve this equation for lambda once you've told what L is, and you'll have the wavelength of the wave, which you can put up here into this equation and solve for the frequency of the speaker sound that will cause this behavior. You'll be reminded that the speed of sound is 340 meters per second. Now, some facts about resonances in tubes that you should know. First of all, this wave equation applies to the sound wave resonance. The second thing is As we've already seen, the distance between consecutive letters is a quarter wavelength, and that for any resonance that's created, at any open end, you have an antinode. At a closed end, there's always a node, and the letters alternate. Never do you have two consecutive N's or two consecutive A's. The product of lambda and F, as we saw here, is a speed of sound, which is 340 meters per second. Now, let's look at a specific example of a tube open at one end, closed at the other. Its length is 0.85 meters. This is one of the virtually infinity of possibilities of a resonance condition that can exist. This particular configuration occurs for the lowest of possible frequency that will cause a resonance. It corresponds to the fewest number of letters you could put along the length of the tube to indicate what is happening. An A there and an N there. Back here, the particular case of resonance we discussed had four letters, AN, AN. Well, in this case, there's only one such A to N segment, and it has the length quarter lambda. So quarter lambda equals the length of the tube. Solve for lambda, and we get 3.4 meters. Well, substitute this lambda into the wave equation here, and then solve it for F, and we get exactly 100 hertz. This particular frequency is the lowest frequency that will cause a standing wave or resonance to exist in this tube. The fewest number of letters corresponds to the lowest frequency. And since that's the lowest frequency that will resonate, the first of many others that will resonate, let's symbolize this as F subscript 1. That frequency, a special frequency, is called the fundamental frequency. The smallest frequency that will resonate in any tube is called the fundamental frequency. It's also called the first harmonic frequency. Harmonic reminds you of a musical instrument or tones. First harmonic frequency, also called the fundamental frequency. Now let's look at the next lowest frequency that will resonate in this tube. It occurs for this configuration here. The next fewest number of letters you can array along the length of the tube, AN, AN. Notice that there are three such special distances we spoke of repeatedly that have a length of quarter lambda. Add them all together, it's the length of the tube, 0.85. Solve for lambda, and we get this, which I don't bother to decimalize. I'm going to leave it in this form. Makes it easier on us later. And that later is now. We'll use this equation here to solve for F. It's speed V, 340, divided by the wavelength we just found here. The 3.4 divides neatly. It's 100. Flip the 3 upstairs. Final result, 300 hertz. Notice that 300 hertz is exactly 3 times the fundamental frequency. And so what we choose to do is to symbolize this frequency with a subscript 3 to suggest that that frequency is triple, 3 times the fundamental frequency. Well, we can keep going like this, and let's keep going up one more time and find the next lowest frequency that will resonate in this tube. And I show the letters that array along the tube, AN, 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 and An. Well, there are 5 such of these special distances, 1, 2, 3, 4, and 5, each being a quarter lambda. Add them all up, length of the tube. Solve for lambda, and you get this value here. Take that value of lambda and put it in the wave equation. Solve for F, and this is what you get. 3.4 again goes neatly into 340, 100 times. Flip the 5 upstairs. Final result, 500 hertz for the next lowest frequency. How shall we subscript this particular frequency? I will call it F subscript 5. By now you might have guessed or seen a pattern. If we were to go and look for the next lowest frequency that will resonate, perhaps you will not be surprised if I tell you it would be 700 hertz, and then 900, 11, 13, 15, 1700 hertz. To summarize what we've seen here for the tube in question, all of the frequencies that will cause a resonance, a loud sound, are odd integer multiples of the lowest. Odd integer, 1, 3, 5, 7, 9, 11, 13. Odd integer multiples of the smallest frequency, which is the fundamental frequency, F1. So there's F1, F3, F5, F7, F9. All of them are the odd integer multiples of 100. Now, in the next video lecture, we'll repeat the same kind of calculation, except remove the barrier at this end of this 0.85 meter tube. We'll have an open tube. We'll go through exactly the same sort of calculations. And I'll tell you now what you can expect to see. In an open tube of this length, the frequencies of the speaker that will cause a resonance, a loud sound, are even integer 2, 4, 6, 8, 10, 12, 14, even integer multiples of the lowest frequency possible for a tube of this length. That lowest frequency we've already found is 100 hertz. So in the open tube you'll next see, in the next lecture, the frequencies that will resonate are 200, 400, 600, 800, 1000, 1200, and so on. Got it?